In this video, we're going to cover our last major topic in our survey of different conservation laws in fluid mechanics, and that's conservation of energy. And energy in engineering systems is very important for a variety of reasons. Two easy examples are if we want to supply water to a city or inject a fuel into a combustion engine, we often need a pump. We need to add energy to the system in order to provide that water, to get it through the system, enough pressure to either volatilize the fuel or to have pressure in your water tap to force water out of it so you can take a shower. Another flip side of that is if we want to take energy out of the system to say power the university, we might use a hydroelectric power plant where we run water from a dam, drop it in elevation to extract potential energy out of the system using a turbine. So a couple of simple examples of why we care about conservation of energy in engineering. And to do this, we're going to do the same thing we did for conservation of mass and conservation of momentum and look at the Reynolds transport theorem. So if we take that generalized form where we had capital B as stuff, we're going to replace that stuff with capital E for energy. And that means that lowercase b, or stuff per unit mass, is going to be lowercase e, or stuff or energy per mass. Okay? And so when we plug that into our generalized form, we get the total change of energy in the system, capital D E over dt, is equal to the time rate of change of the integral over the control volume of rho e dv plus the integral over the control surface of rho e v dot dA. The first thing we want to do is take a look at the left-hand side of this equation, capital dE dt. And we ask ourselves is, well, how can energy in the system change? Because that's what this term is telling us. And really the two things that can happen is we can either add energy through adding heat, or we can let the system do work, and so it'll lose energy. Okay? So if we think about this mathematically, we can write this in the form of the first law of thermodynamics, where we say that the total change in energy in the system is equal to Q, the heat put into the system, minus the work done by the system, W. Okay, so this is the heat added and this is the work done. Okay, so that's just our first, again, the first law of thermodynamics. But we don't want this in its full form. We want it in a discretized form or a rate formulation. So we're going to do that. And so we're going to say capital dE over dt. So that's, again, the left-hand side of our equation there is equal to Q dot minus W dot, where now Q dot is going to be the rate of thermal energy flux, and this is the rate of work done, W dot. Okay, so that gives us an expression for dE dt. Okay, so the next thing we want to look at is what types of energy can the fluid that we're interested in possess. So we're going to start looking, still looking at capital E, but we're also looking now at lowercase e so that we can substitute in some things that we can deal with other than just arbitrary E. Okay, so what kinds of energy can the fluid possess? Well, we've already dealt with a couple of these, kinetic energy being one and potential energy being the other. We saw this in the momentum equation as well as in the Bernoulli equation. And so if we can write our formulation, so basically what we're doing here is we're going to separate out this E into some different terms. So here we have kinetic energy, so we're going to call that capital EK. And we have an expression for that from physics, and we've used it already in this class, is 1/2 mv squared. And then if we look at lowercase e, we're going to say it's 1/2 of the mass times the velocity squared over the mass equals 1/2 times the velocity squared. Okay, so now we have expressions for both of those terms. We've also looked at potential energy already, so that's another form of energy. And here we'll use capital EP. and that is equal to the mass times the gravitational acceleration times the elevation. And there, we can do the same thing, get lowercase e, we get, it's going to be mgz over m, and that's going to equal gz. And then the third type of energy that the fluid can possess is the internal energy. And we're not going to explicitly deal with this in this class very much, but it is important. And the internal energy can be either chemical energy, thermal energy, which we've already touched upon, and electrical energy. And there are other classes where you'll deal with this. Chemical engineering classes will deal with the chemical energy part of the internal energy, as well as thermodynamics will deal with that thermal energy. Okay, but for the purposes of this class, we're going to simply say, we're going to lump this all together. We're going to call this EU, or just U. So this is our internal energy. And we're going to say that this internal energy is just a function of temperature. Okay, therefore if T is constant, EU doesn't change. Okay, and that's just a simplification we'll do in this class, because again, we're really interested for these purposes in the kinetic and potential energy, and some other classes will move on and deal with the internal energy more explicitly. Okay, so once we do all that, we can write out an expression for the conservation of energy using our Reynolds transport theorem. So we're going to say that dE over dt is equal to q dot minus w dot is equal to the integral over the control volume, d over dt times the integral over the control volume of v squared over 2 plus gz plus u dv, right? Sorry, I need a row in there, plus the integral over the control surface of rho v squared over 2 plus gz plus u v dot dA. Okay, so that gives us a full expression for the conservation of energy in the form of the Reynolds transport theorem. The next thing I want to do is look at some of these other terms. So Q is the thermal energy flux. That's a fairly straightforward value that we can get. But the W dot term is the one we don't have a very good handle on. So the next thing we ask ourselves is, how does a volume do work? So how can we define this W dot term? And the first one is by turning a shaft. So if the fluid's turning something, it's doing work on that shaft. So a good example of this is if you did have a water wheel. So you have some water wheel that looks like this and some shaft attached to it, and it's got some paddles like this, and you have a flow going past it and it's turning this shaft like this, then that fluid is doing work on that shaft by turning it as it flows by. So that's, if you ever see a water wheel when you're driving through the countryside, then you're seeing a fluid doing work. Okay, and so this work is positive if the fluid is doing work, and is negative if the shaft is doing work. Okay, so what that looks like, if we write it out, is W dot shaft is equal to WT dot, so the turbine, minus the pump. Again, for a turbine, it's positive because the fluid is doing work. The fluid is putting work into the shaft, which is extracting the energy. It's negative if the shaft is doing work, so in the case of a pump, where the shaft is actually doing work on the fluid. Okay? The second way that a fluid can do work is by changing shape. And this is not one that's not immediately intuitive. We're going to call this W dot F. It's a work of the fluid. And the reason this works is because if we look at our definition of work, so work is equal to force times distance. So this is just, again, going back to physics and looking at our definition of work, which is force times distance. And what happens is as the fluid changes shapes, there is some work done. And I want to spend a little bit of time and show you that through an example. So let's look at the arbitrary flow through a duct where we have a control volume that's outlined here by 1. So this, I've already drawn it in. So we have this control volume, and we're going to let that control volume move in this duct. So at time 1, it has this shape, and at time 2, it looks like the red line. So some later time, delta t, we have the control volume has changed shape because the duct has changed shape. Okay? And so what I've labeled on here are the distance that it's traveled, and because of the convective acceleration as that duct narrows, the surface at 1, the lower surface is going to move a distance of L1, which is V1 times delta t, but the other surface at the other end is going to move faster because it's accelerating more, and so it's going to travel a distance L2, which is going to be the velocity at that point times delta t as well. And then at those two surfaces, we have pressure. So we have pressure at 1 times A1 to get the force there, and then pressure at 2 times A2 to get the force at the other end. I've drawn the pressure out in this case instead of in, which is what we've done more often. And the reason I've done that is because we're looking at the work that the fluid is doing rather than the work that's being done on the fluid. And so I'm using a sign convention where the pressure is pointing out. Only for this example will we do this, and so don't worry about it, but it's really important when we go through the math here. It makes it quite a bit simpler. Okay, so let's look at the work done at surface 1. Okay, so if we say delta WF is equal to force times length is going to be equal to negative P1A1 V1 delta T, right? So a force P1A1 times V1 delta T is the length. Okay? So that WF dot is going to equal delta WF over delta T is equal to negative P1A1 V1. Okay? So now let's look at surface 2. And it's going to be exactly the same. So WF dot at 2 is equal to P2 A2 V2. So exactly the same. And then if we plug that into our equation, we can say that WF dot is equal to, and I'm going to rearrange this slightly, P1 times negative A1 V1 plus P2 times A2 V2. And what you immediately see is this term here is simply V dot dA. Right? Because of the way we've defined our normal to the surface, we actually pull out V1A1 and V2A2 as simply V dot dA. So this is equal to the integral over the control surface of PV dot dA. Okay? So now we can plug this back into our equation. All right, so let's do that. So now we're going to get Q dot plus WP dot, so there's our pump, minus WT dot, there's our turbine, minus the integral over the control surface of PV dot dA is equal to the time rate of change, the integral over the control volume of rho E dV plus the integral over the control surface of rho E V dot dA. Okay, I wrote that in shorthand, but we're going to end up putting this back in as we did before, where we say E is equal to V squared over 2 plus GZ plus U. And then I'm going to rearrange. So I'm going to take that last term on the left-hand side, the integral of the control surface of P dot VdA, and move that into this second term. So what I'm going to do here is just rearrange this slightly. I'm going to take this term and combine it with this term, okay? And then I'll plug this back in to get a final form. So conservation of energy is Q dot minus WP dot, plus WP dot minus WT dot is equal to the time rate of change, the integral over the control volume of rho V squared over 2 plus GZ plus U dV plus the integral over the control surface of rho times P over rho. So now that is the term up here again, this plus V squared over 2 plus GZ plus U V dot dA. And this gives us the final form of the conservation of energy for a fluid. Okay? In the next few lectures, we'll go over the engineering formulation of this equation. So engineers, we've actually simplified this and rearranged some things to make it a little bit easier to use. And then we'll look at some examples of how we would apply the conservation of energy.